Hello everyone. So today my goal is to review the chapters that are going to be on the midterm, which is coming up on Wednesday. And there's a bunch of stuff, and rather than like furiously scribbling all this down, I'm just going to use the review that I did last semester, which is I think pretty much what I wanted to do again. So, and of course, like last time, I will post this PDF on GitHub so you guys can have it yourselves. But by going through this without scribbling, I'll have more time for questions if there are any. So again, the coverage of the exam is units 5, 6, 7, 8. Nothing on the deep networks. And unit 5 is where we started talking about classification. We focused on logistic regression in that case. So just to start, how do we define classification? We predict categorical label Y from some features X, given training data of XY pairs, I going from 1 to n. So in the binary case where we have either Y equals 1 or Y is not equal to 1, so Y could be 0 or minus 1. If we have two features, then we have an illustration like this, where we have like feature x1, x2, and we have two colors of labels. Maybe these are the y equals 1s, and the green x's are the y equals not equal to 1. And in this case, we would like to build a decision region which tells us which region of the feature space we will find the y equals 1 samples and which region we won't find them. So that's the goal of classification, is to come up with that decision region. As you can see in this picture, the decision region is not a line, so we would consider this to be a nonlinear classifier. We spent most of our time in this unit, however, talking about linear classifiers. For linear classifiers, we have a slightly different picture where the boundary that gives us our classification regions is linear. So, and in more detail, in binary linear classification, we can think of it as a two-step process. The first step is to compute a score, which we call Z, just a real number, that is the bias B plus W transpose X. So here W is a vector of our weights of the same dimension as the number of features in X. And so this number Z will be larger, closer to positive infinity, the more confident we are that the label is 1. And the more confident we are that the label is not equal to 1, the closer Z will be to negative infinity. When Z is exactly 0, that means we just have very little confidence either way. We don't know whether it's a 1 or minus 1. That's the point of least confidence. Once we have this score Z, we can just simply threshold it. We choose some value t. Often t is 0, but it doesn't have to be. And when z is greater or equal to t, we declare that our estimate of the label y hat is 1. Or when z is less than t, we declare that our estimate is not equal to 1. And we did talk about how to choose t. And we found that choosing t equals 0 is what we want to do if we want to maximize classification accuracy. That's not always our goal. We'll talk about other goals in a little bit. So that's just a review of binary linear classification in its most general form. The key point we haven't talked about yet is how to come up with our weights B and W. To figure out what those weights are to train this classifier, given this data, we need to develop some sort of model for how X relates to Y. In this unit, we focused on the logistic model, which is a probabilistic model that says that the probability that Y equals 1, given the score Z, takes this equation 1 over 1 plus e to the power minus z. So that function, if you think of it as a function of z, is this sigmoid curve. It goes from 0 up to almost 1. It finally hits 1 as z goes to infinity. and it takes on the value of 1/2 when z is 0. So again, that would be the place where we have the least uncertainty. The probability that y equals 1 is 1/2 when z equals 0. So based on that model, that's the model we would like to use to learn our coefficients b and w. And the way that we do this is the procedure we keep using over and over again, which is maximum likelihood estimation. So we first state our likelihood. Here we're assuming that all the samples y are going to be independent, given the score z. And so the likelihood is the product across all our data samples I, the probability of yi given zi. And that is closely related to this equation here. The tricky thing is that when we put in y not equal to 1 here, this expression changes. And so it was a little bit challenging to come up with one expression for this. So when we did the derivation, we came up with some switching variables that sort of, they turn on and off two forms of this. One of them turns on when y equals 1. The other turns on when y equals not equal to 1. And we went through a derivation, and we eventually figured out that maximizing this likelihood is the same thing as minimizing this, which is a sum over all our training samples I going from 1 to n, of the natural log of 1 plus e to the zi minus yi zi. So this is the expression that holds when yi is 0 or 1. We had a slightly different expression when yi was minus 1 and 1. And we gave this the name binary cross entropy loss. So this is finally how we train our model, how we come up with the weights b and w. Later in Unit 7, we came up with an alternate way of doing this based on the support vector classifier. But for now, Unit 5, this is how we said we're going to do it. So again, this is all for binary classification. When we have more than 2 classes, we talked about other options for us. Are there any questions so far? Okay. So,
Excuse me.
yes.
Like the arc on I it actually is a negative on what
Is there? You think there's a typo somewhere? It's
I
the
think there should be a minus sign.
minus this whole thing.
Yeah. Negative.
Oh, up here, or just everywhere?
Before the log.
For the log. Oh, let's see. Let's go back. Oh. Uh-oh. Sorry, I messed something up here. Okay, sorry, so let's just do that. Okay, so this is the expression. I think I have that correct. Right? Is good? Okay. Okay. Yeah. So that's what we derived. Okay, everybody good with this? Okay, so then when we have more than 2 classes, we have to start with saying, how do we do linear classification in that case? So the approach that we developed is based on this one versus rest idea. And what we do is, instead of having a single score like we did in the binary case, we actually have capital K scores when we have K classes. And then each score essentially tells us how confident we are like the score z little k tells us how confident we are that we are in class little k. And so when we look at all our scores as a set and we want to say which class are we most confident about, we just look for the value of k that gives us the maximum of all our scores. So that's our y hat in this case. And each of these zk's, to compute that, we have a separate bias bk and a separate vector of parameters wk that matches x in terms of the number of features. Now, again, the next question is, how do we decide on the weights and the biases in this case? So we talked about first a simple method, which is based on this one versus rest idea. And what we do is we go through the different values of little k, and let's say we start with B1, W1. We trained that pair alone using binary logistic regression. So to do that, we need to look at our training set. We need to sort of split it into two pieces. One are the features where y equals 1, and then that's one half, and then the other half is the features for all the other k's. So split our in total, let's say we have 3 or more classes. We're going to split it into two pieces where we have 1 and not 1. And then we train that. And then we split it again into 2 and not 2. And we split and we train it. And then 3 and not 3, and we train it. So each time we're training this pair separately using binary logistic regression, exactly how we described above, but just on different partitions of our data set. So that's certainly one approach. It's relatively fast, but a possible weakness is that we are not training all the biases and all the weights jointly. We're just training each pair separately. So we also talked about another approach called multinomial logistic regression, where they are trained jointly. And to train them jointly, we actually need to come up with a model that's an extension of our binary logistic model to where we have more than 2 classes. And so this is our new model. Sometimes we call this the softmax. We can think of this as a mapping from a vector of capital K real numbers to a probability mass function, or in this case to a single probability. But if you expand this over the different k's, you get a vector of probabilities where all those probabilities sum to 1, and as probabilities they're between 0 and 1. So when we look at that vector, we can tell exactly how confident we are in the different possibilities k. So we get a probability mass function. So that's what this softmax does. And we can use maximum likelihood estimation to do this. So now we just, instead of like using the binary one before, now we use our softmax, our multinomial model. We maximize now a vector of b's and a matrix of all these different weight vectors. And we go through that, and we derived an expression. I didn't write it down here, but the expression is sort of an extension of this, and that would be called the cross entropy loss. So that's those are really two options that we have here. And what we tend to see in practice is that this multinomial logistic regression works a little bit better. However, it is more expensive to train. And so in practice, we have a trade-off between how expensive we want it to be and how well we want it to work. And I think the project will be a good example for you guys to see these trade-offs and how much longer it takes, how much better it is, and so on. Okay, any questions on MLR? Okay, so then we came back to the discussion of performance metrics. And starting with just the binary case, we said that there's different ways to make errors, and different ways to measure the effects of making those errors. So the one that's most common is just to focus on maximizing the accuracy. And the accuracy is just the probability that your guess, y hat, is equal to the true y. But sometimes accuracy hides the situation that, let's say I have a data set where 99% of my samples are label 1 and only 1% of my samples are not 1. Now, if you give me this data set and I tell you I can get 100% accuracy, you shouldn't be too excited because I can get 100% accuracy by completely ignoring the feature vector and just always predicting label 1. So in such a case, you don't really want to maximize accuracy because that's not a very useful metric. You might want to maximize something like precision or recall. So precision is the probability that y equals 1 given that the true label equals 1 given that your guess equals 1. Recall, you flip it, you say what's the probability that your guess equals 1 given that the true label equals 1, and so on. And there was sensitivity and specificity and a few other ones as well. Now, sometimes it's insightful to plot precision and recall versus each other on this chart. And what you'll find is that as you change this decision threshold, this was the number t over here, as you change the decision threshold, we'll come back in a sec. Okay, as you change the decision threshold t, what happens is you get a different set of performances where you can essentially trade precision for recall. So actually there's different ways to make this plot. In this plot, we're not showing precision and recall. We are showing probability of correct detection given y equals 1. And, sorry, I don't know why this is happening. And the probability that y equals 1 given that the true label is not equal to 1. So this is known as the false alarm rate. So this is another very common way to plot performance. And what happens is as you increase your decision threshold, your false alarm rate decreases, which is good, but then your probability of correct detection also decreases, which is bad. So the place you want to be is up here, where you have high probability of correct detection, low probability of false alarm rate. And as you can see, you have a different set of possible performances depending on how you choose that threshold. Now, what often happens is you don't want to make a specific choice on your threshold at the time that you train your classifier. So you might instead say, I actually just want this curve to be as close to that corner as possible. And one way to measure that is look at the area under the curve, the AUC. The area under the curve is something that, in the ideal case, when the threshold is up here, would be 1. In the worst case, if you're guessing, it would be 0.5. And so in practice, it's going to be somewhere between 0.5 and 1. So this metric is a much better metric when you're in that imbalance situation where, like the case I mentioned earlier, where you have 99% ones and 1% not ones. And if you want to design a good classifier in that case, accuracy is not going to be a good thing to use, but area under the curve could be a good thing to use. And you don't even have to decide what final threshold you're going to use when you design your system. You can design that later after your system is trained. And this is, in fact, the metric that I set up for the final project, right? You guys, I think it's already posted, so you saw it. So in that case, that is your goal. Your goal is to maximize area under the curve. And it's really not so different from maximizing accuracy. You train your model the same way. So notice that, when I train my model, I'm actually just training according to this logistic loss, binary cross entropy loss. At this point, I'm not saying I care about accuracy, I care about AUC. I'm just saying I care about this loss. So you can train it with that loss. Now, when someone says, how good is your model? Once it's trained, then you can evaluate it according to these different metrics. And since AUC is implemented in sklearn, it's pretty easy to just pop in that line of code and see what is your AUC. So if you're doing something like cross-validation, at that point you do want to use AUC instead of accuracy to do your hyperparameter tuning. That will make a difference. But in terms of training your weights, that is done using those MLR or binary logistic regression losses. Okay, is that pretty clear? Okay. So any other questions? Any other questions on Unit 5? Yes.
So, what if, like, in the case when your true positive rate is 0, so for one class you're just not even predicting it at all. So in that case, your AUC metric will basically give you 0 for that class. Like, and
So when you say your true positive rate is 0, that would be for a certain choice of threshold. So that would be like 1 point along this curve.
yeah,
But right, so the AUC is actually a metric that you evaluate before you make the choice of the threshold. It's because each one of the points along this term would correspond to a different choice of threshold. So when you maximize AUC, it's a threshold independent metric. It's a metric that should work well for a range of choices of threshold, which you will make later. If that makes sense.
but
I don't think you're going to get a model where no matter what threshold you use, you're always getting 0. That'd be very bad. I don't think that's going to happen.
no, but like if the threshold is like way up or like a higher value, then you're getting lesser area under the curve. So
No. So again, the threshold would be like a particular point on the curve. So if you tell me the threshold t, then I will show you a point on the curve to which your t corresponds to. And for that particular t, I could tell you what is the true the true detection probability and the false alarm rate for that t. But now you can see that the AUC is more than just that t. The AUC is measuring every possible t that you could choose. So the AUC is measuring the area under this curve. And the curve is defined by all possible threshold choices from minus infinity to infinity. Does that make sense? Yeah, okay. Okay, good questions. Any other questions on Unit 5? Okay, good. So let's move on to Unit 6, optimization. So one of the main concepts in optimization that we started out with is the gradient. So if we have a parameter vector W with D entries, and if we have a cost that we measure the cost of that parameter vector, and by definition our cost has to be just one real number, then the gradient of the cost with respect to that vector is going to be a set of partial derivatives that has the same shape as the parameter vector, and what it does is in each location it just looks at the partial derivative. In this first location, it looks at the partial derivative of j with respect to the first cost entry. The second would be the partial derivative with respect to the second parameter entry, and so on, all the way down to the last one. So this is the gradient, and it's a very useful quantity for optimization. And basically what it does is it tells us the slope and the direction of maximum increase of the cost at that parameter location W. And so we proved this notion. So the slope would be given by the norm of this vector, and the direction you would get, if you just look at which direction this is pointing, that would tell you the direction to which you want to move to maximally increase your cost. So, the main way that we use this is if we have a smooth cost or a cost that's differentiable where we can compute this quantity everywhere, then we somehow initialize, maybe randomly, call our initialization W0, and then we do this iterative procedure where you take your current initialization, you take your gradient, which is a vector of the same size as W, and then you multiply it by a minus, which means now that rather than pointing uphill, it's pointing downhill. And with a small step size, now it's pointing downhill, but its norm is just a small vector, short vector. That is the adjustment you make to your current W to get your new W. So in other words, you start randomly and you take small steps downhill, 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 downhill. And if you ever reach a local minimum, eventually the gradient will go to 0 and you will stop moving. And you will have found that local minimum. So a few things we talked about is, number one, if your cost is not smooth, meaning if there's locations where you cannot compute a gradient, then this would not be a good approach to use because you just can't compute the gradient there. We also said that there's a few things to worry about. If you start, let's say, at a global maximum or even a local maximum, that because the gradient is 0 there, you will never move from your initialization because this will be 0 for all time steps. And it's possible, though often unlikely, but possible, that you could, as you're minimizing, you could converge to a saddle point. The saddle point is a location in your cost function where along one direction you have a positive curvature, along another direction you have a negative curvature, and at exactly that point you have 0 gradient. So you could converge to the saddle, and once you get to the saddle, your gradient goes to 0 and you will stop moving. Typically, that's not what happens in practice. What happens is you get close to the saddle, but in getting close to that saddle, the gradient flattens out and you get stuck there for a while where you don't really move much for a while, and then eventually you fall off and you go to a better location. But these are some of the issues that one has when applying gradient descent in practice. Okay. Another thing we did is we verified that, assuming the cost is smooth, that if the step size is small enough, sufficiently small, that we will make progress in minimizing our gradient or minimizing our cost. So here we have less than or equal to, so this is the cost at the new location is less than or equal to the cost at the old location. We need the equal there just because it could be that you're at the optimal location anyway, so there's no way to decrease it further. But typically what you see as in practice is this is a strict less than. The way that we proved this is we looked at some expressions for the cost. We applied some Taylor series approximations and some this big O, which is sort of an order analysis term. And we showed that this is the new cost equals the old cost minus or plus a negative term and a positive term. So overall, to make progress, we want that this whole thing is negative. And that means that this should overwhelm this. And what we said is, if alpha is small enough that when you square that alpha, it gets super small. So you should always be able to find an alpha for which this term is larger than this term, and therefore this update will be overall negative. So that was the idea. We convinced ourselves that when this is small enough, gradient descent makes progress. Yes?
Sorry, what is the meaning of the last bar, the O?
The big O?
Yes.
So let's see if I want to state it correctly. So let me go back to the notes. Okay. So this is the meaning. So again, just for context, this was our Taylor series approximation. We have a function j. We do the Taylor series at some reference point w naught. We have the gradient at w naught times the perturbation from w naught, and then another term which collects all the higher order terms in the Taylor series. And we're basically saying that this last term is dominated by this difference squared. And so when we're talking about this big O, if you say big O of some epsilon squared, so this would be like our epsilon squared, this means at most a constant times epsilon squared when epsilon is close enough to 0. So it has sort of a dense mathematical meaning. If you've taken a course in real analysis, you see a lot of this type of stuff. You have these epsilon delta type statements where you say there exists some constant c and some epsilon, both positive, such that the function which we're saying is order epsilon squared, this function of epsilon is less than or equal to c times epsilon squared for all epsilon in this interval. So again, it's a bit of a mouthful. It's something that maybe you want to sit down and look at it for a bit. But it basically tells us that this is dominated by by the squared term. A little bit of intuition is that when this number is less than 1, if you take the cube it's even smaller than the square, right? If you take the fourth power, it's even smaller. So the one which is the most important is not the cube and the fourth power, it's actually the square. That's the one that matters. This is the linear term, and this is the square term. And essentially, for any function, you know, there's all these terms, squared, cubed, quadratic, and all that, but we're just saying that's a distraction. We don't really care about all those terms. We just want to sort of upper bound it by one term, which is proportional to the square distance. And this is how we build that upper bound. Okay. Okay. Okay, so that was how we convinced ourselves that gradient descent works if the step size is small enough. And then that brought us to the question of, well, how do you choose a step size if you never know how small it should be in advance? And we came up with this approach to adapt the step size on the fly as we iterate. And this was this Armijo method. And it goes like this. At each iteration t, we perform a gradient descent update, and then we check to see if this condition is satisfied for the given, you know, for the current w, the current choice of alpha t. If you find that this is satisfied, then you say, I've made enough progress. Great. You accept that iteration, and you move to the next iteration. And in fact, what you do is you say, since it worked this time, maybe I could get away with using a larger step size next time. And so if yes, you might double the step size, you might increase it by 1.1, so just increase it somehow, and then try again with the next iteration. And as long as things keep working, you just keep increasing your step size, and this is a nice way, if you initially chose your step size too conservatively, too small, you will eventually increase it up to the point where it fails. And now you know, I've gone too far. This will fail, and now you say, let's throw out that update because it was a bad one. Let's decrease our step size. Maybe we, chop it in half, and then try again. If this fails again, it says, okay, I didn't change my step size, didn't decrease it enough, so you decrease it even more. When it eventually passes, then you go back to this, yes, I'm going to double it, and so on. These numbers, 1/2, 2, this 1/2, these are all adjustable parameters that you can play around with as you like, but maybe 1/2 works pretty well for this. For this, I would personally use something closer to like maybe 1.1, and then maybe 1/2 for this. So this is the Armijo method. It's one of many methods out there that are designed to adapt the step size. It's just a pretty famous one that's taught in a lot of intro optimization courses. Okay, any questions on Armijo? Okay, and then the last thing we talked about is what do we get with a convex cost function? So with the non-convex cost functions, we could get into situations where we have local minima and global minima. And in that case, if we initialize near a local minima and we take small step sizes, we will converge to a local minima, and we will be disappointed because we haven't converged to the global minima that we really wanted to converge to. But when we know that we have a convex cost function, we don't have to worry about this stuff happening. We essentially know that every local minima is also a global minima. So here's one case, quadratic, where it turns out that this local minima is unique. But it's not necessarily unique in convex optimization. So here's another case where you have a convex cost, and you have many minima, but they're all equally good. So all your local minima are global minima. This would be a case where we don't have differentiability. Maybe we have to use another technique, not the gradient-based methods, but just to show you that maybe it's not unique, but they're all equally good. And then finally, we recalled a few cases where we saw convex costs so far in the course. So RSS that we studied for regression back in units 1 and 2, that's quadratic, that is convex. Logistic regression from unit 5, that's convex. Anytime you add either L2 or L1 regularization to those costs, it still stays convex. And in the next unit, the hinge loss for the support vector classifier, that also gives us a convex loss. Same thing when you add L2 and L1. So we actually do get to see a lot of different convex loss functions in our course, but when we get to our neural networks in Unit 8, we no longer have convexity once you have those nonlinear activations, it's not going to be convex in the weights and biases that flow through those activations. So in that case, it's a difficult problem. Neural networks are known to have many of these local minima, and so we try to use other optimization methods that might use momentum or some other thing to bounce out of the bad ones and land in a good one. Okay, so that's it for Unit 6. Are there any questions on anything? Okay, great. Let's move on to Unit 7. Support vector classifier, support vector machine. So here what we started by doing is we started by taking a closer look at the geometry of linear classification. So again, we have our features, in this case x1 and x2. This is just the case with two features. All the geometric ideas extend to generically D features, but it just becomes harder to draw them. It's enough to draw the two features and you get all the intuition you need. So now we're dealing with linear classification methods, which means our classification boundary is linear, it's a line. And the first thing we realized is that in this linear classifier framework, the weight vector, W, is always going to be orthogonal to the boundary. So if you tell me the weight vector, I can tell you where the boundary is up to some shift. To nail down what the shift is, we need to know what is the bias coefficient. Now, if you tell me the bias B and the weight W1, I can tell you exactly where the boundary crosses the x1 axis. If you tell me B and W2, I can tell you where that boundary crosses the x2 axis and so on. So we know, number one, that we have this orthogonality. We can also nail down exactly where our boundary crosses our axes. And one thing we noted with this is that if you scale both B and W, then the boundary doesn't actually move at all. It stays in the same place. Okay, the next thing we talked about was if we want to look at the distance from a point to the boundary. So let's say this is my point here, and I want to know how far is this from the boundary. So what we said is what you do is you move in the direction that takes you quickest to the boundary. That's the same direction as the W vector. And you can just measure how far you have to move in that direction until you're on the boundary. And based on that idea, we derived an expression for gamma I. Sorry, okay, it's coming back. Okay, we see gamma I, which is this expression. So this is the signed distance from a training point xi to the boundary. It's a signed distance because as you look at this, you can see that it could be positive or negative. So when you're in the sample, when you're on a training sample xi that corresponds to a positive label, y equals 1, you're going to have a positive cost. And if you're corresponding to a negative label, you have a negative distance, not cost distance. Okay, so this was something we used in the next step. So the next step is we recalled what linearly separable data means. So just geometrically, it means that my training data is such that when I plot these two classes, that it's possible to separate them cleanly with a boundary. And so this, as you can see in this example, the boundary is, the data set is linearly separable. We have this boundary. And you can see there's many other boundaries which will separate it as well. But the other thing we looked at is we came up with a specific mathematical definition of linearly separable that basically said that if you multiply the label, so in this case, the label, we assume that this was yi is either 1 or minus 1. We assume that for the analysis just because it made everything a lot easier. So when that's the case, so remember that this is the score. You want that the score times the label, or the sign corrected score, is greater or equal to 1 for all I. So we said that it's enough to think about linear separability this way. So notice that we're looking at a particular number on the right side, not epsilon, which allows us to come up with a B and a W that are of a particular size for this to hold. So that, with that idea, we said that this sign-corrected score is greater or equal to, sign-corrected sign distance is greater or equal to 1 over the norm of W. That, in other words, whenever your data is linearly separable, you can find a W vector such that this happens. And we gave this 1 over norm of W a special term, the margin, gamma, and we can visualize that margin as the distance from the boundary to the closest samples. And so for robustness, we said we would like to make our boundary as far as possible from the closest samples. If I make it too close to those samples, even though it's still linearly separable, when I have test data, it's not going to be exactly where my training data is, and my test data might be misclassified if I don't make a robust selection of my boundary. So we want to try to put the boundary as far from the nearest training samples as possible, and that led us to this hard margin classifier. So here we're looking to find the B and W that minimize this norm squared, which is the same thing as maximizing this margin, subject to our linear separability constraint. So we really need this for this 1 over norm W to make sense, to be meaningful. Okay, so this was sort of a good initial starting idea, but the problem is that the only way to satisfy this constraint, which holds for all I, is when your training data is linearly separable. So in practice, in a lot of cases, we don't have linearly separable training data, which means we cannot apply this idea. So we said, well, we can actually make a slight modification of this idea that preserves what we like about this, but also allows us to apply this to non-linearly separable training data. And the idea was to take this constraint and reformulate it as a cost. So here we're looking at the max of either the number 0 or the number 1 minus yi. So again, you can see that by noticing that this is our zi. And so 1 minus yizi would be like 0 is greater or equal to 1 minus yizi. Right? We can get that from that inequality. So we would like this to be smaller than 0 if possible. And anytime it's greater than 0, it will add to this cost, and we will see the effect of that. So we were looking to try to find a W that keeps this term at 0, which would mean that all our training data is linearly separable. But at the same time, by also minimizing this, it's going to push this boundary so that it's nicely located as far as possible from the closest training samples. Now, in the case that it's impossible to linearly separate the training data, it's okay. It means that this part of the cost, you can never force it to 0, but you can still try to make it as small as possible. At that point, you have to make a trade-off between how small you make the first term and how small you make the second term, and you can do that by choosing this number C. This is some positive number. Basically, as C increases, the margin decreases. So that allows you to increase or decrease the width of this street. And as we discussed, there's sort of a trade-off between bias and variance. The narrower the street, that means the fewer the training samples are involved in defining that street or that boundary, which means that the boundary is very sensitive to a few training, and therefore you have a variance issue, high variance. On the other hand, if you decide to instead increase this, now your boundary is going to be affected by many more training samples, which means there's going to be less variance, less variation across different experiments. However, when you involve all these other training samples, you give up on the idea of determining the boundary based on only the closest ones. And so now, maybe the street changes and you get a bias problem where all of a sudden some of these samples are close to the boundary or maybe even misclassified. So we have this bias variance trade-off, and we said the way to navigate that trade-off is actually to use cross-validation, k-fold cross-validation or whatever. Okay, so that's how we got this. And finally, the other thing we noticed is that the boundary that is made by this technique will only depend on some subset of your training samples, and you call those the support vectors. Those are the xi for which this quantity is less than or equal to 1. Okay, so so that was sort of where we ended up. This is called the soft margin or the support vector classifier. This is a nice idea. When we did experiments comparing it to logistic regression, we found that it generally worked a little bit better, not a huge amount better, but it was a little bit more robust. So that wasn't the end of the story. The next chapter in the story was we want to improve this a lot, and we can do that by using some sort of nonlinear transformation. The transformation we call as phi of x. This is a transformation we apply to all our features. One way to think about it is maybe I can just apply some transformation to all my features before training, and then I just train things in the usual way with a support vector classifier. That's a possibility, but the downsides of that are often this transformation is something that increases the number of features. So maybe you go from a few features to having many, many features. And in that case, you have other problems with bias variance trade-off. As we know, the more features you have for a given data set, the higher your variance becomes. And so generally speaking, if we can avoid increasing features, we would like to. In fact, when we studied model order selection and feature selection, our goal was the opposite. It was actually to decrease the number of features so that to reduce the variance. So here, we're possibly adding features, which is somewhat dangerous. So as another approach, we rewrote the support vector classifier using this dual form. And in the dual form, we saw that when we use one of these transformations, we always have terms of this form, phi transpose phi. And so we said if we just redefine those terms in terms of this kernel function kappa that takes in two arguments, these two x's, then we can actually avoid explicitly defining a transformation and instead just build a kernel directly that compares these two feature vectors and tells us how similar or different they are. And that led us to a technique where we could use things like this radial basis function kernel, which essentially just looks at the L2 norm difference of the vectors, exponentiates it. This is the most popular one. And if you try to start here and figure out what is the phi vector that corresponds to this, you find that the only way you can do that is actually build an infinite dimensional phi. So obviously that's something we could never do with phi directly. However, with a kernel, we can do it quite easily. We can work with this, and the optimization algorithm is tractable and everything. And then when we applied this idea to the training data, we saw a huge increase in performance. I think with our MNIST, we went from like 91 to 97% accuracy. So that was a huge advance. And basically these support vector machine methods they were more or less state-of-the-art 15 years ago before neural networks had their latest resurgence. So these are good methods, and I think on the project, you'll find that they perform quite well, maybe competitive with the neural networks you design. But that's up to you guys to try to improve all these methods. When you use these, you do have to make two important choices. You have to tune your kernel bandwidth alpha, and you have to tune your C. And actually, you have to do those together. And you have to choose those numbers carefully with cross-validation to really get the maximum performance out of these methods. You can also do other things on the project. You can use feature selection. You can do other things to try to improve. The more you do, the better things will get. The better you'll climb in the Kaggle leaderboard. All right, so the very last thing to talk about, just quickly in the last few minutes here, is Unit 8. The last unit on the midterm is on neural networks. Basically, we're just looking at 2-layer neural networks, and we can think about this as follows based on the last unit. Can we somehow learn a feature transformation phi from the training data itself without having to use an idea like this that someone gives us that might not work that well with our given data set? And the answer is yes. We can do this by building, you could say the second stage looks just like our linear classifier. Often we train this with logistic regression, so it's basically like Unit 5. But then we build a first stage that essentially learns an explicit phi function such that the features we give to the classifier are approximately linearly separable. So maybe we start out with some training data X. As you can see in this picture, that's very far from linearly separable. You can see that all the zeros are in the middle, all the X's are on the outside. So with a linear classifier, with this alone, we could never do a good job with this data set. But with this first stage, in this case, we're using 3 hidden units. Each one of them is, we can think of it as giving us like a linear classifier output, which we know is defined by a linear boundary. And then we can, so each one of these guys basically splits the data into you're either on this side or you're on that side. And once you have 3 of them, you can look at the intersection of those 3 subspaces or half spaces. And using the second stage, you can say, I'm looking for the things which are in this intersection. And in doing so, you can create, as you see, a nonlinear decision region, and you can do well with this data set. So in this case, we're actually learning how to build the transformation from the data samples themselves. And so that's kind of a nice idea. And essentially, that's kind of the idea, the simple kernel of an idea behind all these neural networks. You can get, you have things to decide, like what exact functions do you use for these nonlinearities? Are they going to be sigmoids? Are they going to be something else? That changes the interpretation a little bit, but overall, things work in a similar way. So finally, once we make some architectural choices, like what are these functions, how many are there, and so on, we have to train our parameters, which are in this case these weights and biases in the hidden layer and the output layers. So we put those all together in theta. We define our cost that uses our training data and our parameter hypothesis. Typically, we would use something like logistic regression on these output scores, and then we just do gradient descent on the negative log likelihood cost. So this J here, or actually this J here would be the negative log likelihood. The derivation is very similar to what we've seen before, except for the extra complications and the fact that we have gradients, we have these nonlinearities which sort of affect how these different parameters manifest in our cost. So to figure out how to compute those gradients, which is the main challenge now, is we constructed this computation graph, which just showed how all the variables are related to each other. So on the right side of our graph, we have the cost, J, from here. And on the left side, we have our inputs, our xi's. And to start, we do the forward pass, where we take our xi's and our current weights and biases, and we pass the information through the network, and we construct all these different, we compute all these different numbers. And then for back propagation, we learned about an organized method where we can start on the right side, proceed leftward, and compute all the gradients. At the end, we want to compute the gradients with respect to our parameters. So we used basically the idea behind the multivariate chain rule, which is to say if you want to do dj db, you do dj dz, dz db. And then the thing you have to figure out is when there are a number of different variables at this intermediate node, does the variable you are differentiating in respect to, does it affect multiple of them or just one of them? If it affects multiple of them, use this multivariate chain rule where you sum up across all the different paths through those different variables. However, if it just affects one of them, then you can use the single chain rule where you don't have a sum there. But otherwise, we worked through in detail how you do the backward pass, and eventually you get like your DJ, DB0, DJ, DWO, and so on and so on. So, so with that, we're at exactly 5:05. Those are the ideas that are fair game for the midterm. I haven't made the midterm yet, so I have no idea what will be on it. Are there any questions on this last unit? Great. Okay, so I will post these to GitHub, these notes. Did you have a question? Or okay. And so exam will be in here on Wednesday. I look forward to seeing you guys then. If you have any questions about lecture notes, please post them to the discussion board. Try to get them answered right away. See you on Wednesday.